Okay. One thing that is important to keep in mind is that there's a basic difference from the DRAM and the SRAM architecture, as you already know, but it's worth repeating. Of course, in the case of DRAM, the information is stored in the charge which is on the capacitor of each memory cell. And of course, these capacitance in practice are leaky, in the sense that this charge gets lost. So the capacitors gets discharged in time, and therefore naturally lose some information. And for this reason, independently of the read operations that are necessary, there is always a process going on in DRAMs of so-called refreshing the memory. The process is called refresh. Basically, there's a finite state machine which in turns addresses all the memory cells, and reads the information on each memory. And does this process because when the information is read, there is this restore. The sense amplifier starts, and the voltage level on the capacitor is completely restored. So it's a sort of background process when the memory is not accessed for read or write operations. This process in turn access all the memories just in order to refresh the voltage level on the capacitor. This is something that is needed for the DRAM, and of course it's not needed for the SRAM. Okay. We need to mention something regarding the architecture and the layout, the different possibilities that we have for the layout area. And of course, if we look at this scheme, the comparison bit line must be a bit line which is not accessed by a read operation. So a bit line that has all the word lines not active. And this can be obtained in two different ways, with the so-called open memory array or with a folded memory array. For example, in the open memory array solution, we have that the array of the memory is split into two parts, and we have the sense amplifiers in the middle. So for example, we need the sense amplifier for each pair of bit lines. Let's assume that these small rectangles here are the sense amplifier. For example, this is sense N, and this is sense N negated, and this is VDB. So we have several sense amplifiers. So these are the sense amplifiers, and in the case of the open memory array, each sense amplifier is connected to a different bit line, and one is the bit line of one half of the memory, and the other bit line is on the other half of the memory. So one is the bit line and the other one is the comparison bit line. The bit line and the comparison bit line, of course, the two roles can be exchanged. And then we have all the word lines that go in this direction. So these are the word lines, and of course these red ones are the bit lines. Why this is important? Because you see that the bit line of the upper part are connected to different word lines with respect to the bit line of the bottom half. Okay, so that since we know that only one word line is active, when one word line is active, for example the first, we can use this other bit line as the comparison bit line, because none of the word lines that are crossing it are active. Okay? So for every bit line is activated, the other bit line which is connected to the same sense amplifier but to the other half of the memory bank is the comparison bit line. This is one solution. The other solution, they are both quite common, is the so-called folded memory array. Folded memory. Array. So in this case you do not have the memory bank split in two. You have all the sense amplifiers on the side. For example, as in this case you have the sense N and sense N negated here. But then the bit line are all on the same side. For example, here, and here, 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 here. Yeah. Okay, so they are all on the same side. Of course, in order to use always one bit line as the comparison bit line of the other one needs to be sure that the word lines do not cross all the bit lines. For example, one does the following thing. Let me use the green for the word line as before. Let me just draw 4 word lines. And in this case we for example have in this position a bit line, but here for the second one we have no cell, and but we have a cell here. Okay, here we have no cell, and we have a cell here. And we have no cell here. And for the other bit line we have the cell in correspondence of the other bit line. So here we have one, here we have the other one, here we have the other one, and so on. Okay, again, for example, if the first word line is activated, then we can use the other bit line as a comparison bit line, because there will be no other word lines crossing this bit line that are active. So this is the difference. The main difference with respect the main difference from the open memory array and the folded memory array are in terms of two aspects. Typically, this is denser, and it's not clear from this drawing, but it is denser because in the open memory array, for all the crossing, we have a memory cell. For the folded memory array, we have, for half the crossings, no cell. So in practice, the number of cells per unit area is smaller for the folded. Is smaller for the folded memory array. This means that the open memory array is denser. I wrote denser in the wrong place. The open is denser. So, let me restate it. The open memory array is denser because we have, this is denser, because we have a memory cell in each crossing, and for the folded memory array, we have a memory cell for half the crossings. So this is denser. And this is one reason why the open memory array is sometimes preferred. Sometimes not really always, because this is something that is not obvious, but the open memory array is more sensitive to the so-called substrate noise. Because sometimes there is a local disturb in the array, for example, a coupling through the substrate to some variation of the voltage in circuits that are close by. And in this case, the open memory array is more sensitive because, for example, if I have some noise here, okay, in this region, and I compare the value of the voltage on this bit line and on the other bit line, then I can make a wrong comparison because this noise can affect the value of the voltage on the bit line which is in the bottom part of the memory. So I make an error in the reading of the information on the memory cell. Okay? Consider that the sense amplifier must detect very small differences in voltage, so even some small disturb or some noise can alter this reading. In this case, instead, the situation is different because the two bit lines that are comparated are very close together. So if there is some noise, this noise is very likely to have the same effect on the two bit lines, so that it has no effect on the difference, and therefore the reading operation is more robust. So this part is more robust to noise. And this is the reason why sometimes it is still used. Okay, now the issue is how large can these memory arrays be? And it actually depends on some constraints on velocity and on power consumption. Let's consider first the power consumption. So the power consumption that is important here is the power consumption of the sense amplifier. How do we address this part? Essentially, the energy consumption of the sense amplifier during a read operation is due to the energy that the sense amplifier has to spend in order to charge the bit lines. Okay? So the energy is C tot of the bit line. This is the total capacitance of the bit line times VDD square over 2 times 2 because we have 2 bit lines. Okay, this is the energy. This is the energy per read operation. Okay, if we multiply this by the frequency of read operation, which is the average number of read operations per second, so this is frequency of read operation. So if I multiply the energy of a read operation times the frequency of a read operation, I obtain the power required for the read operation of one sense amplifier. If I then multiply times the number of sense amplifiers, I can obtain the total power consumption of the memory bank. So this is the total power consumption of the memory bank. It is not actually the absolute total, is only the total of the components due to the sense amplifiers, but is the most important one. And therefore, you see that this is something that is limiting the if I want to limit the power consumption, I need somewhat to limit the length of the bit line, because the length of the bit line increases the total capacitance of the bit line. And I also have to limit the number of sense amplifier, which is the number of bit lines, which is the other dimension, the length of the word line. Okay, so the if I want to limit the total power consumption, I have to limit the dimension of the memory, the length of the bit line and the length of the word line. So P is proportional to the length of bit line times the length of the word lines. And both of them are proportional to the size of the memory array. Okay? There is also an additional aspect which is connected to the time required to activate the word line. Let me write here. Time required to the time required to activate the word line, of course, is a part of the total read time. Okay, remember, the total read time consists of the sum of the pre-charge time of the bit line, then the activation of the word line, then the operation of the sense amplifier. Okay, but the time required to activate the word line is limited by the fact that the word line if I consider a word line, what I have is a set of gates of MOSFETs connected to the word line. The situation is like this. This is one bit line, this is the other bit line, then we have another bit line. So the word line is a conductor connected to a series of gates, each of them and each of them has a capacitance with respect to ground. So this is equivalent to having a conductor and then some capacitances, the gate capacitance of each MOSFET connected to ground. So I have a total capacitance of the word line which is something like, in order to simplify, the number of bit lines that are crossing the word line times the capacitance of each gate. This is the total capacitance of the word line. And also the word line has a resistance, because typically is done for technological reasons. The word line is done with polysilicon. Typically a particular type of polysilicon with a small resistance, which is called silicide polysilicon. So there is a layer of silicide on top of the polysilicon in order to reduce the resistance. So this is silicide polysilicon. But in practice has a resistance which is larger than the resistance of a metal. And therefore I have to take this resistance into account. And the resistance, of course, again is proportional to the length of the word line. Which is, of course, proportional to the number of bit lines. So I can simplify the word line in electrical terms as a single resistance, which is the total resistance of the word line, and a capacitance towards ground, which is the sum of all the gate capacitances. This circuit, of course, has a delay, a time required. If I apply a step voltage, the time required in order to let the voltage arrive to the full value is a few times the RC constant of the circuit. So is limited by this RC constant, which is the product of R and C. It's typically 2-3 RC, 2-3 time constants are sufficient. But if I just want to keep the discussion at a very qualitative level, the read time is limited by tau, and tau is limited by the length of the word line. Okay? So there are two reasons not to have the word line too long. One is the power dissipated by the sense amplifiers, and the other one is the time required to activate the word line. And in practice, these two factors are limiting the number of bit lines to half 1,000. Typically, since they are all powers of 2, the max number of bit line in practice is 512, and for the considerations of power, in practice also the maximum number of word lines is again 512. So this means a memory bank of 256 kilobit. Okay? So this is the typical size of the array. Of course, we need much more memory than that, and this means that we have to duplicate the circuit for as many times as required. Okay? So let me repeat, two considerations. The delay time for charging the word line, which limits the read time, and the maximum power consumption of the sense amplifiers are limiting both the number of bit lines and the number of word lines in a memory bank to a practical number of 500. Okay? If we want to have a larger memory, which of course we need to put many banks. Let's say we have to make an array of memory banks. So to duplicate all the word decoder, the bit line decoder, the sense amplifiers, every 500 word lines and every 500 bit lines. This is still what is happening in practical circuits now. Okay. So I want to spend some minutes just to show you how in practice are all these memory cells packed together. And I already anticipated the fact that the capacitor is obtained by drilling a hole in the silicon, so is a vertical capacitor. But let me draw the layout and the cross section, just to let you understand what is the situation. So one thing that is important to keep in mind is that typically for a given CMOS process we have the definition of a minimum feature size that we can use. This is called typically F. F stands for feature size. And for many CMOS technology is equal to the name of the technology. So for example, if I use a 45 nanometer technology, it means that the minimum feature size that I can have is 45 nanometers. Okay? And this is also useful to understand how things are actually scaling. Let us consider, for example, an open memory array. And let's consider how we can make everything as compact as possible. You know that in an open memory array, you have a memory cell at each crossing, and from the circuit point of view, if I take two adjacent word lines, such as this, and for example 1 bit line, I have here one cell, and I have here the other cell. Okay. Now, in order to save space, it can be more convenient to have only one contact from the transistors to the bit line. So this is word line A and word line B. And it is useful to draw the circuit first. And so what is typically done is the following thing. We refold these two transistors in this way. Typically have you see, this is exactly the same circuit, so that, but the only difference is that we have only one contact. Okay, this is something that simplifies a bit the circuit and makes everything much more compact. Let me show you here how compact can this be. So the two word lines, we make the two word lines with poly of a minimum feature size F, and between the two word lines we have this contact with the bit line. So the bit line is this one. Okay, so this is the bit line. And this is the word line. This is the word line. And for example, let me write in red, we have a certain separation, and here we have another bit line, and so on. And then here we have the source of the transistor, and in correspondence of the source of the transistor we make the capacitor. This disk represents the capacitor. Here is the capacitor here, and that's it. So let me draw here below the total then we have, so let me write, this is F, this is again F, this is again F, and so on, and this of course continues. I don't want to draw everything, but this is just a part of the array. And below it's the same thing. We have a separation of F here, and then again have the rest, the other bit lines, the other word lines, and so on. Everything is repeated from here on and also above. This is just the single cell. Now the total size is the following: is 2F on this direction, and here I have F again. F is this size. This is F. This is F, and this is F also the spacer. So I have 6f. So in this rectangle, 6f times 2f, we have 2 bits. So the area per bit is 6f times 2f over 2, which is 6f squared. And this is something, of course, that scales with the technology. If f is 0.1 micron, I can compute the area of 1 bit. If f is 0.32 micron, for example, I can compute the area of a bit, and therefore the density, the number of bits per unit area that I can have. This is typically the minimum size of a DRAM. The hard part, as you can probably imagine, is having the capacitor, which is completely vertical. So we have to dedicate some time to discuss how this capacitor is made. But this is the capacitor. So you can recognize here the gate. This is the drain, gate, source. In correspondence of the source, we have the capacitor, which is this: drain, gate, source. It's really, and as you can see, the area occupied by a memory cell is essentially only the area of one transistor, because the capacitor is below the source of the transistor and therefore does not occupy any area. Okay? In the case of the folded memory array, of course, when you write 6f squared, we are not considering the space, the area occupied by the sense amplifiers. But in practice, that is negligible if we have a large memory bank. Okay. If we consider the folded memory array, just let me look at this part. You see that the difference is that in the folded memory array, you have a memory cell only in correspondence of half of the crossings. And in the case of the other half of the crossings, you don't want anything. You do not want an electric contact, and in practice you also want you only want electrical insulation. So what happens is the following. Basically, you have the 2 bit lines, for example, 1 and the other one. These are the bit lines. Let's call bit line A and bit line B. Of course, one of the bit line is used as the actual bit line, and the other one is used as the comparison bit line. And then if I consider the word line for 1 bit line, the situation is exactly the same that I draw before. So there are the 2 gates here corresponding to the word lines. Word line 1, word line 2. This is the contact with the bit line. Then we have the 2 capacitors. Okay, this is the part that we have already drawn. But then we also have here 2 additional word lines that are not connected, that are just passing over the bit line without any actual interactions. Okay, because for half of the crossings we do not have any contact. Okay, but of course these two word lines, let us call them 3 and 4, will have to be connected to the gates on the following bit line. So in the case of the following bit line, here we have here we have a contact, here we have the two capacitors, and of course in this case the other two word lines will not correspond to any gate, because there are no actual devices in the crossing between the word line and the bit line. Okay, and so on. So this is the contact. Let me erase this and redraw it. This is the contact. Essentially, this is the contact between the drain of these two transistors and the bit line. And of course, this thing is repeated again and again. So I just want to draw 4 bit lines, but of course I can repeat everything for the other cases. If I want to, let me use another color to draw the other, I will have something like this. Other 2 memory cells here, and then of course we will have something like here we will have another, etc., etc. Okay, these 2 are going to be like this. Etc., etc. Everything is repeated. Now, if we want to compute here the memory area, you can see it is larger because we have 2 additional crossings here. So, if this is F and this is F, again we have here 2F, but then the vertical dimension of the cell is F plus F plus F plus F plus F plus F plus F for the other 2 word lines. And therefore, if we sum everything, we have this is there's an F for the space. We have something like 8F. So the memory area, the area of 1 bit is 8F times 2F divided by 2, because we have 2 bits in this 8 by 2. So it's 8F squared. As I was mentioning before, it's of course less dense than in the previous case. Okay, so now maybe with this drawing it is clearer what I said before. In the case of the open memory array, we have a denser array, essentially because we can have a memory cell for each crossing, whereas in this case we have a memory cell only for half of the crossings, and therefore we use the area less efficiently. Now, just let me just consider a cross section. Let's do it in this direction, just to understand how this memory cell is done. Essentially, we have this situation. This is the M plus region in correspondence of the contact, and then we have above it we have one transistor, and below it we have another transistor. So we have this situation. This is the gate, and this is the word line. So this is the word line. Let me draw it in red. Okay. This is the word line. And then here we have the source, which is connected to the source is N+, which is connected to the capacitor. The capacitor has this shape, goes below, that there's a drill. This is drilled in the MOSFET, and essentially there is this N+ region here, which is one electrode of the capacitance. Then there is the electric layer in the middle, and then there is some poly in the middle, which is essentially a filler, is the other electrode. So we have the electric here. So in order to obtain the capacitance and to have a large area for the capacitance, we obtain the area by drilling a hole below the transistor. So from the top you see something like a circular footprint. Okay, here we have the contact with the bit line, which passes above everything. So this is again an insulating layer, insulator, and this is the bit line. We can draw the bit line. The bit line is metallic. We can draw it in blue. So the word line, the capacitance, the contact, and then on the other side we have again another word line. This is the electric and this is the other word line, and then we have the other capacitance. So this is again N+. So there is the source and one plate of the capacitor, and then the dielectric and the other plate, which is in the hole. This is the second word line. For example, this is word line 1 and this is word line 2, and so on. So in practice the array is quite simple. It's convenient to have the word line that are passing below the metal lines and therefore are polysilicon stripes, and we have metal lines for the bit lines. So the key to the success of the DRAM actually has been the capability of fabricating these vertical capacitors. Okay, because actually only the fabrication of vertical capacitors could allow to have a very small area for each memory cell. Now, just to close this part, I mentioned that we have a maximum size of the array, which is 512 times 512. If we need larger arrays, we need to combine this smaller ones. So max bank is 512 times 512, which means 256 kilobit. Okay, if we want a 1 gigabit DRAM, which is not that large, of course we need to have a large number of banks, because we need to have, let's say, 4 banks to make 1 megabit, and there we need 4 K banks. We need 4K banks. Okay, so a pretty large array of banks. How do we do that? We typically do the following thing. We have 1 bank, then we have the row decoder and the column decoder, or the word line decoder and bit line decoder, and then we repeat the same structure again and again. Row decoder, column decoder, another bank, and then below you have the row decoder, another bank, the column decoder, and on and on. Everything is repeated 4,000 times. So RD stays for row decoder, is also the word line, the word decoder. Okay, and CD stays for column decoder, which is the bit line decoder. Only 2 things I need to mention on this regard. One is obvious, is that of course this arrangement let's say implies a loss in area occupation, because typically, as you can see also in this simple drawing, a large fraction of the total area is not occupied by the memory array, but is occupied by the decoders and by some let's say space which is not efficiently occupied. So the area efficiency of typical arrangements is something like 50-60%. Okay. By area efficiency, I mean the ratio of the area which is actually occupied by the memory banks and the area which is occupied by the periphery circuit, the addressing circuit, and so on. Okay. So, with respect to the 6f squared that we computed before, if we want to calculate the total area occupied by the memory, we take that number and more or less multiply by 2, because the periphery circuits will occupy an area which is more or less as large as the actual memory array. This is one consideration. The other consideration is that, of course, this arrangement provides some possibility for parallelism, in the sense that, of course, since we have independent row decoders and column decoders for each memory banks, we can, at least in principle, read or write different memory banks at the same time. Okay. Of course, this implies some, let's say, complications in the addressing circuits, but in principle it is possible. It is, of course, done because when we read 64 bits, we read 64 bits at a word of 64 bits, we read the 64 bits at the same time, not one bit after the other. but of course also some additional parallelism is in principle possible. I say in principle because it is not always used, because of course it has some costs. So let me write here only parallelism. Let me write more completely. A degree of parallelism is possible. Is possible between parentheses read or write different memory banks simultaneously. Okay, let's make a break.